All right, here we go. Lecture number 5, continuing review of general linear models and linear mixed models. I'm going to be writing more today, and I don't know what you guys, how you learn best, if it's sitting there and looking at what I'm doing, or if it helps you to write. I know some people, you kind of get more engaged when you write yourself. So whatever, I record this and I write it down. So that's a benefit. So you don't have to write stuff down, but if you learn better by writing, I encourage you to do that. So I'm going to be writing more today on top of the slides. So foundational material, see other document. Actually, I'm going to jump that. Maybe at the end, I'll see if we have time to do that. So we're going to talk about a bunch of stuff today that covers basically writing statistical models, and you guys have done that. So this is kind of a review, and we can see if we're on the same page as far as the way we write models. There's different ways to do it. G inverses, generalized inverses. Have you guys, just a quick show of hands, how many people are familiar with generalized inverses? Not at all? You didn't talk about this at all in 6612? Wow, okay. Okay, so it's a new thing, it's not review. Estimability, do you guys remember that topic? Maybe some of the stuff you talked about really quickly or something, I don't know, maybe not. Key theorems and identities that are going to be useful. Writing custom tests, we'll spend some time on that, and then we'll talk about modeling time as a class variable versus a continuous variable, and I'm sure that's more of a review. So this is a mixture then. Some of it's not review, and that's part of the reason why we do this is, if it's reviewed, good, that it pounds it in even more, but if it's not, then you're seeing something that you probably shouldn't have heard about at some point. So means models versus effects models. Does that ring a bell? Okay, good. So there's different ways to formulate the model, and one of the distinctions is writing a means model versus an effects model. So let's say we have a situation where we have two groups and 3 time points. So here we have time 1, 2, and 3, and group 1 and 2. Okay, and you can think of the mean, think of this combination. The first time point for the first group, you're gonna be interested in estimating some mean for that. So we can call that mu 1, 1. For the second time, you can say mu 1, 2, and so forth. Seems like if I don't write straight down, this happens here. Let's just try to mu 1, 3, and so forth. Okay, get the picture. So writing a model for this, we could do, we have 3 elements that we need to be concerned about. We have subjects involved in this, we have time, and we have group. And so normally for longitudinal model, we write Yij, right, where I is subject and J is time. But in this case, I'm going to actually add something because we have group as well that's kind of important. So we can go H, Ij, that's our outcome. And I'm using indicators there for, again, for group, subject, and time. And those need to be represented on the right side as well. So for a means model, it's pretty simple. We have the mean, and we have group H and time J, and we have an error term here. And here I'm just gonna write IJ. So one of the key things for this model that I'm writing is that the indicator I accounts for all subjects in the data. And that way, I don't need to worry about adding the H on the epsilon as well. The other thing too, if this is longitudinal data, say that we'll account for repeated measures through the R matrix. So we have E sub I, which is going to account for, that's a vector, right? And that's multivariate normal, mean 0, and covariance matrix R sub I. So R is going to account for the repeated measures, okay? So you can specify, I'll just say we can specify R. You know, it could be, if we only have 3 time points, then, you know, we could do like an unstructure for R, or we could do the AR1 or compound symmetric structure. And so that's the means model. Why? Stay. Okay, so if I press this, I erase it. I'm learning some new things here. I'm pretty stubborn, so I'll get it figured out. That's the means model. Okay, and the effects model is going to take that mean and it's going to break it down into components, like you can express your group effects, your time effects, and your group by time effects. So for this model, we start out with the same outcome, Hij, but instead of writing mu, just an overall mean, we can break that down into mu, and then we have some effect for group. I'll call that alpha, and then the indicator for which group we're considering, and then we have our time effects, and usually we're going to add an interaction term to allow, you know, this is the most flexible model possible that we can have. And then we have the error term. So everything else is the same. What we've really done is we've just re-expressed this mean into different components, and that's the effects model. So you guys hopefully are familiar with that. You know, so it's really the same model, just a few different ways to express that. Any questions on that? Okay, so moving on. Yeah.
That mu is just the grand mean, right, among all groups and times in the effects model?
You can think of that as an intercept. That like when you actually fit the model and you get your output, it will say intercept for that. And you could write that as beta naught or whatever. It could be the grand mean, but it depends on how you specify the effects in the model. It might not necessarily be the grand mean.
Okay.
It could be though. Again, depending on how you specify the model. So that's a good question. So full rank, another question?
Can you give an example when it's not the grand mean?
Um, yeah, so, and we'll talk a little bit more, but it depends on what constraints you put on these, the alpha, tau, and gamma effects. Like if you constrain them to be, there's, okay, so this opens the can of worms that we need to talk about. So it's a decent question, but when you have a model like this, right, and you have, we have two parameters essentially for group. We have alpha 1 and alpha 2 because there's two groups, right? And how many for tau? How many parameters do we have there? See if you're with me.
2.
2?
Wouldn't you have 3 minus 1?
Well, yeah, so there's 2 that we can estimate, you're right. But there's 3 in this model, the way we've written the model, there's 2 for group and there's 3 for time. But you've jumped ahead of me, you're thinking, and you know that there's a constraint that we have 2 degrees of freedom. So you're right, we can only estimate 2 of them. But in the model that we've written here, we've actually made a parameter for both groups, for 2 groups, for 3 times, and for 6 interactions. Okay, so for this model, we actually have, so I'll clarify, H is 1, 2, J is 1, 2 to 3, and I, we don't know for sure, but I'll just say that goes up to N, okay? So this is what we call a less than full rank model because we specified more parameters than we can estimate. Okay, and you guys have probably got pounded on in 6612 that if you have a class variable, one of them has to be the reference level, right? And if you use SAS, it's going to be the highest level, it's going to be set as the reference level. If you use R, the first one by default is going to be the reference level. That's one way to deal with the constraint, okay? Now, if you use those approaches, that intercept is not going to be the grand mean. It'll be the grand mean if you set the constraints a different way. If you set the constraints so that the sum of these other effects, the alpha, tau, and the gamma effects, the sum of those are 0, which is another way to do the constraint, then that mu is going to be the overall mean. Okay? So we have to deal with the fact that we don't have a full rank. If you were to write the X matrix and you were to include a column for both groups for 3 time points and for the 6 associated interaction columns, then that X matrix doesn't have full rank. Okay, so full rank, is that a term that sounds familiar to you guys? So to have full rank, what we do is we eliminate one of the columns, we make it the reference level, right? So you're going to have 1 column for group, you're going to have 2 for time, and then you'll have 2 for the interaction, and then 1 for the intercept. And that allows you to make that full rank X, and then you can take your regular inverse. But if you're using the less than full rank model, let's say the group is gender, so let's say men and women, okay? And you have a column for each one, and then you have columns for the 3 time points, and you create that X matrix. It does not have full rank. That means that there's linear dependencies in that matrix. An alternative way to do the analysis is to use a generalized inverse, which you can compute even when X does not have full rank. Okay. Now, in previous years, I spent a little more time on this issue. We talked about it and I gave more homework questions. This year, I think I'm going to streamline the approach and just, it'll be more of a sidebar. But there's a lot of detail in the course notes that you can go and read about. Whether you deal with the constraints up front and set 1 to 0 and make a full rank model and use a full rank X, or whether you use a generalized inverse. Those are two general different approaches that you can take for estimation. And I'll leave it at that. So, you know, the software does it for you, right? What it seems like it's doing is setting one of the columns to 0, right? So again, the reference level is, for SAS, it's the highest level set as the reference level. And for R, it's the first typically by default. But actually what's happening is it's using a generalized inverse. And it just so happens that it's equivalent to the set to 0 approach, okay? So that's the can of worms that I had to talk about a little bit, you know, when you asked the question about the intercept. But it's something that, you know, I did want to talk about. So to continue a little bit on with that, you know, we have the full rank and less than full rank models that we can write. And, you know, you may be more familiar with one of these than the other, which is fine. But I want you to know both. And the reason why is not because I want you to necessarily write both, but I want you, you know, you can write it whatever way you want to write it, and that's fine. But you might see it a different way. And so you need, when you see it in the literature, you need to be able to understand that there's different ways these models can be expressed. And so here's one example where we're looking at a study where we have, this time we're going to model time as continuous. And we have 3 treatment groups. We have treatment A, treatment B, and control. And we're going to add the group by time interaction. Okay. So, so the question for you is, if we have time as continuous and we just have a linear term, then what are we essentially doing when we fit this model? We have 3 different groups. We have the interaction. Can you explain to me what we're doing in our estimation of, you know, whatever outcome that we're observing? You know, maybe it's lung function or symptoms or something like that. And we're observing how that changes over these 3 time points. We have 3 groups and we have the interaction and time is continuous. So what are we, can you explain to me what this model is estimating and how we're comparing these 3 groups? It's a little bit open-ended, but see if you can answer that one. If you only had one group, what would you be doing? What would you call it?
Are you making the assumption that the time distances are, so the interval between each time is equidistant?
Sure. Yeah, we'll make that assumption that the equally spaced time points. You have one group, continuous time, fit a model. What do you call that? Did you say, Carrie? Go ahead.
The linear line.
Linear regression, right? That's linear regression, simple linear regression. Now we add a couple more groups, right? And so we have a line for one group. We have an interaction term. What does that interaction term allow us to do for the different groups?
Change the slope.
Say again, Chloe.
It allows us to change the slope.
Yeah, exactly. So we have different slopes for each group. So essentially we're fitting lines to each group over time, and we can compare those to each other, right? And that may be the thing that's of interest. Are these slopes different for each of these groups? And the interaction is a thing that will tell us whether those slopes are different from each other, right? And so one way to write the model is basically to create indicators right? And this is maybe a way you're familiar with doing it. So x1 is going to be time, that's a continuous variable. x2 is going to be 1 for treatment A and 0 otherwise. x3 is going to be 1 for treatment B and 0 otherwise. And then we only need 2. So the control is going to be the reference group, so we don't actually add anything for that group. Does this approach, is this the way you learn how to write models in 62612? That's pretty standard. So we're using indicators. If we have a class variable, in this case it's group, then we deal with that, the fact that, you know, one of the indicators would be dependent on the other. So we only need 2 of them, right? And we've dealt with that potential linear dependency just by not including an indicator variable for the control group. And in this case, we have beta 1, that's the slope for time, and x1 is going to be continuous variable. Okay, so this is one way to write the model, and for that we have 6 beta coefficients, right? So we have 6 fixed effects in that model, and if this is a longitudinal data, we're taking measures over time on subjects, we could specify, just like we did before, the R matrix, you know, to account for the repeated measures, or we could add random effects. You don't see them here, but that's another way we could deal with the repeated measures. Okay, an alternative way to write that model is this way, and in this case, we have k sub h is going to be, that's what I'm going to use for group, and this term here is what I'm going to use for group by time. Okay, so the gamma h times x1, that's the continuous x, and then this here is for time. So in this model, we have beta naught, we have beta 1, h could go from 1 to 3. So we have kappa 1, kappa 2, kappa 3, and then we have our interaction coefficients, gamma 1, gamma 2, gamma 3. How many parameters we have there? There's 8. So there's eight fixed effects here in this model. And so we've actually written a parameter for the control group. And so this is a less than full rank model. And we end up, eventually we need a way to deal with that linear dependency. But we've actually, in this model, written a parameter for all of the potential values for those class variables. Okay, and you'll see that. You'll see this model written in different places. So it's just good to be familiar with that. And yeah, any questions? I'm not gonna, like I said, I'm not gonna spend as much time talking about these things, but I think I at least need to bring it up. It's kind of important, and I may talk about it a little bit more going forward, but probably not as much as I had in the past. So in computing estimates, the issue with less than full rank models, so that's what LTFR stands for. Less than full rank, is that if we include a column in X for each of the C levels of a categorical variable, X will not have full rank, nor will X transpose X, and hence a regular inverse cannot be used when calculating the estimator for beta hat. So there's two basic approaches, like I mentioned before. One is to force a constraint on the model up front, either set to 0, that's probably the most common when you run SAS or R. There's a set to, well, it seems like there's a set to 0 constraint. We actually use the generalized inverse, but it ends up being equivalent to that. You could also do a sum to 0, and in that case, then the intercept is going to have a more, it will be more interpretable. You know, it'll be the overall average. And in that case, X is going to have full rank, and you can use the regular formula. And the second approach is to introduce a new type of inverse, a generalized inverse, that will handle the singularity issue. In some cases, these approaches are essentially the same. So, for example, SAS's G inverse is essentially like setting the highest levels of factors to 0. There's a lot more detail on this in the course notes, if you're interested in that. So what is the issue with estimability? For less than full rank models, beta hat is not unique and depends on the G inverse used. So the theory of estimability tells us which linear combinations of parameters are estimable in that model. So the question is, why do we even need to worry about this? Why not just use the approach that we learned in 6612? Well, by using the less than full rank model, which is actually what's done, I know that's what's used in SAS and probably in R as well, then you don't need to worry about manually creating indicator variables. You can just put in a class variable for race or gender or group, and that linear dependency is going to be taken care of by using a generalized inverse. And it also makes, you know, calculating contrasts and estimates easier. You can keep the levels of all variables and put in whatever coefficient you need for all the levels. So I think it's a little more intuitive when you use it. And like I said, this is actually the model that's fit. We actually create an X matrix with a level for each variable. You put in a column for each level that you have for that variable in the X matrix. So what we need to do is we need to figure out some linear combination of the parameters that are estimable, and there's a lot of theory on this and on how to do this. So if you enter the E option in the model statement, SAS is going to tell you what functions of the parameters, what linear combination of the parameters are estimable. Okay, so that's a really quick overview of estimability. If you write an estimate or contrast statement and it's not estimable, SAS will tell you this is not estimable. And I don't know if you've run into that issue before, but that happens a lot. If you're writing custom tests or estimate statements, it'll tell you if it just can't do it. Okay. The next two, was there a question that somebody?
Yeah.
Yeah.
So you're saying in the background, R and SAS are always using less than full rank models, but just figuring out the parameters through the generalized inverse?
Yes.
Then how come the output always looks like it's done with the full rank model? Because they never include like all the, they don't include the reference category.
I can tell you, I'm loud, aren't I? Because I can hear you through when you, and you guys are smart, you know how to turn on and off the thing. So, so that's a really good question. I know SAS uses a generalized inverse because it says it does. And I'm assuming that R does as well. But it, you know, I don't know for sure how R works, but I do know for SAS, it fits a generalized inverse. And the thing is that, like I said real quickly, is the generalized inverse, there's many different generalized inverses that you can use. The one that SAS uses just so happens to look like a set to 0, where the highest level is 0, but it's really using a generalized inverse is what it's doing. It just so happens that it turns out being equivalent to the set to 0 approach, with the highest level being set to 0. There's other types of generalized inverses though, like the Moore-Penrose generalized inverse, which is not a set, it's not equivalent to a set to zero. So you actually get estimates, non-zero estimates for all of the levels. But again, since you can pick different generalized inverses, the solution's not unique. And you may have seen when you run proc GLM that you'll get a note at the bottom saying, be careful, the solution here is not unique. You may have seen that in the past. And so that's why we need to worry about what are the linear combinations of the beta parameters are unique, and correspondingly, what are the estimates, what combinations of the estimates are unique, so that we can estimate that linear combination of parameters. So there's kind of a subtle nuance there, you know, between these methods that I'm talking about. And I think that it's good to, I would encourage you guys to read the more detail that I have in the course notes. But I also want to make sure that we spend enough time on other things as well. So I'm trying not to spend a whole lot of time on this, but just enough to tell you that, you know, there's other types of inverses, there's generalized inverses, and actually we'll talk about it just a little bit more here. But what I'm going to do here is present two useful, I don't know what you call them, identities or theorems. The linear form and the quadratic form, identities are results that are very, very useful. These things are going to be important. I don't know if you talked about them in 6612 or not, but if you have a multivariate normal distribution for y, so y has, you know, that's a vector, has mean mu, has some covariance matrix sigma. If you take a matrix A and you multiply A times Y, that also has a normal distribution. And the mean of that is A times mu, and the covariance matrix is A times sigma times A transpose. And so one quick way that you can see this is useful is if we consider this estimator beta hat, and we talked about this last time, where beta hat, if you can actually get the algebraic form using maximum likelihood estimation for the fixed effect estimators. And this turns out to be, see if I can remember it. X transpose, normally just take X transpose X inverse X transpose Y. That's if we have a general linear model. When you have a mixed model, we add in the V inverse there. So it's X transpose V inverse X, that whole thing transpose, and then X, not quite right. I shouldn't just try to do it off the top of my head. That's the lesson. This is inverse, and then this is X transpose V inverse Y. So that's what it looks like for a mixed model, and that's what I presented when we talked about maximum likelihood estimation.
So it's only an inverse if you have full rank though, right? Your X transpose V inverse X, that's only an inverse if you have full rank. Otherwise it is transpose, correct?
So the V, we're based on our model, V is symmetric, and V is always going to have full rank. So that one we can always put the -1. That's a true inverse.
But the first stuff in the brackets,
that's the dash that I use. That's to indicate that it's a generalized inverse.
Okay.
Now, if X has full rank, then this dash that I wrote in the superscript, that'll become a -1, and that'll be a true inverse. So what I've done here is I've written a more general form. And like if you go to the SAS help documentation, you'll see this form. Okay. Now, if X has full rank, this dash will become a true inverse, a -1 in the subscript. So that's an important point to talk about.
So if you multiply a pseudo inverse by itself, do you get the identity matrix, or is that only a property of true inverses?
That's only a property of true inverses.
Okay.
Okay, so that's a really good question. For a G inverse, and I'll write this because I was going to get here anyway. So for a generalized inverse, we know that so that always holds for a G inverse. For the what we call the Moore-Penrose G inverse, we also have this. Okay, so that's really important though, that if you just have, we know that if we take a regular inverse and we multiply the regular inverse of X times X, what do we get?
The identity matrix?
Yes, I was going to say this is a layup. This is okay. We also know that so I have basketball on my mind. I've been watching the Nuggets, and so that's probably why I do my basketball analogies. So this is also the identity matrix. But if you have, if we have a generalized inverse, that doesn't necessarily hold. So I'm sorry, this, take away the one there. So if that doesn't necessarily equal I. Or, okay, we can't make that assumption like we could with the regular inverse. Okay, so we're going to actually, we'll see that when we do this proof. So we have this quantity for beta hat. This is how we calculate beta hat. Okay, now how can we apply this linear form that we're talking about here? It looks different, right? So how do we express or pack this into this result up here?
Do you multiply the mean by everything that's before y, and then
well, we may do that, but what we have to do before we even are concerned about that is we have to figure out how this linear form result is going to apply to this quantity, right? Any thoughts on that? It's just a naming convention, really. What if we take this whole thing here and we call that A? That's just, if we take a bunch of matrices and we multiply them, we're going to end up with a matrix, right? And as long as that matrix satisfies the conditions, the whatever regularity conditions we have, then that'll work. Okay. So this is the beauty of this result, is we can figure out we have a linear form involving y. So we have beta hat is a times y, where a is equal to all this stuff. So you can figure out what the mean, we know that beta hat has a normal distribution, and now we just have to figure out what a times mu is and a times sigma times a transpose. Okay? So the question is, what is mu and what is sigma? We know that y has this form, right? And we talked about the distribution of y last time. So what is mu for a linear mixed model? For you know, the y outcome, marginal mean.
Is it 0?
No, not quite. So we want to take the mean of y, right?
Right.
So you can think of the mean of y when you have expected value, that'll work through those things that we're adding. Getting closer. This is a point where I have to slow down and make sure you guys are, I got you engaged. I don't want to lose you here. The mean, so y has a distribution, right? We know that because we created a maximum likelihood estimator, you know, a likelihood function for it. So we have the distribution of y is normally distributed with some mean and some variance. And the conditional distribution of y, you know, if you condition on the random effects, that has another normal distribution with a certain mean and variance. So what is the mean? So this, in other words, the expected value of y so think of taking the expected value of those three pieces, right? The expected value of the errors, we know that's 0, right? What about the random effects? Well, the B has a normal distribution. What's the mean of that?
I thought it was 0.
Yes, you're right about that. It's 0. So the mean of epsilon, the mean of z times b, those are 0. You're right. But what are we left with?
X beta plus
Yeah.
0.
Right. Now, before, I thought you said beta. Did you say X beta or did you say beta?
X beta.
Then you're right. I just
Well,
didn't hear you. So yeah, you did get it. You're right. I thought I heard beta. So you're right. This is X beta. That's the mean. And the variance of y. Remember that one?
ZG, Z transpose
Yeah.
plus sigma squared.
Yeah, more general is going to be R because we could have, you know, some other type of R matrix specified, but it would be sigma squared times I, you know, if we had the simple R structure there. Okay. So I'm not going to do this whole thing. Like, this is actually question 4 in your homework, is the variance part of it. I'm going to start it, but you guys will finish it. But we'll do the mean. Okay. So we need to figure out, we know that beta hat, that's based on this linear form result, that's normal with mean A times X beta, right? I plugged in what mu was, and the variance is A, and I'm going to keep it simple here. I'm going to use the expression, we just call that V. So I'm going to say V A transpose. So that's what the distribution is. So all we have to do now is just matrix algebra to figure out the mean and the variance, right? So so for the mean, we have X transpose, that first part, X transpose V inverse X beta. So that's equal to beta, right? Or not?
Doesn't your first inverse have to be a true inverse?
Yes, yes. And that's why I was asked you a leading question that was not correct, and Jonathan got it. That's what we talked about up here, is that you can't make that assumption, right? If it's a generalized inverse. Now, if X has full rank and this becomes a regular inverse, then that stuff will all become I, so it'll be I times beta and it'll be beta. But we can't make that assumption. So that's actually how you have to leave it. That's the mean. Okay. Again, when X has full rank, it'll simplify down, and the mean of beta hat would be beta, which is good, right? That means beta hat, when X has full rank, beta hat is unbiased for beta, and that's what you want. So what you have to do then is find the variance. And so really that question 4 now becomes an algebra thing, okay? And so why estimability is important is that you find L times beta hat, where where the L beta is unique, and then we're dealing with a distribution that has that doesn't depend on the G inverse that you use, okay? And that would be another good exercise, find the distribution of L beta hat. And so maybe I'll find a way to stick that somewhere, like on a quiz or something. I don't know, I'm still thinking about that. But, you know, this question, that question 4, then, you know, does require you to know a little bit of matrix algebra. And, you know, in 6612 or before, you know, if you had linear algebra, you probably had some of it. I don't spend a lot of time in this class on matrix algebra, but I do want you to know some of the basics. So, you know, we can talk more probably in office hours if there's any specific things that you need to know about matrix algebra, you know, the kinds of things that you would need to like finish this, you know, this question 4 to get the variance of beta hat. But what this shows us is that beta hat, if we're using a less than full rank matrix, that does not have a unique mean, okay? And so we need to, again, we need to be concerned about what are the linear combinations of the parameters that are estimable. Okay, so that's one of the things that this shows us. There's a similar result called the quadratic form, where if y is a multivariate normal, then y transpose ay has a chi-square distribution. And so that's going to be useful for like if we're dealing with the distribution of sigma hat squared. So for the GLM, the general linear model, we know the form of this looks like this. It's Y transpose times I minus P of XY over N minus K, where P of X, that's the projection or hat matrix that you call it sometimes. That's equal to X times, oops, X transpose X inverse X transpose. So you may have heard the name hat matrix, and it could be an H, you know. I call it projection matrix. I like that name because what you're doing is you're projecting matrices onto the column space of X. So I like that interpretation of it. But you can see this as a quadratic form. In this case, A is equal to I minus P of X. Okay. It follows that form, then we know it's got a chi-square distribution. And we can apply that if we're going to do tests about the variance. Okay, but that's for a GLM. Custom tests. So we'll take the last 20 minutes or so to talk about, you know, writing custom tests. And the basic tests that we do for a mixed model are just like for GLM. We have F tests and T tests. And so when we use one or the other, well, if you have one degree of freedom, use T tests. You know, if you have one L vector, one linear combination of your parameters that are of interest. If you have multiple equations, like for example, if you want to do a test for the interaction usually has multiple degrees of freedom. And so then you have to make a C matrix that has a number of rows to it in order to conduct that test. And then you'd use an F test. Okay. I'm starting to pixelate a little bit here. I don't know if you guys see that or not, but as long as you can kind of still see me, I guess that's the main thing. I'm not sure why that happens. It gets tired. So as far as writing tests, let's consider a two-way effects model. Kind of like what I'd written before. You know, the way I'd written it before, I'd actually used epsilon ij if I is if it's unique across the data that you have.
Do you mean if like
But we're,
they can't be in multiple groups, like compared to like a crossover design or something?
yeah, so like if we had, let's say we had two groups, right? And we use I equals 1, 2, 3, 4, 5 for the subjects in that first group. And then for group 2, we go back to 1, 2, 3, 4, 5. That would be an example where they're not unique across a study. But if we have 10 subjects, and regardless of the group they're in, we label those subjects as 1, 2, 3, 4, 5 up to 10 with that index. Then we can do this. We can write this as epsilon ij.
In practice, wouldn't you just make them unique? As long as they're not like the actual same people, like in a crossover design.
Yeah, I think you would. Yeah, you would. So like normally like the ID should be unique. I think that's a smarter way usually to label subjects so that regardless of the group they're in, they have a unique ID in that study. Yeah. Um, that is just bizarre. Let me do this. Okay. So so for that model, if we have 2 groups and 3 times, like we talked about before, here's the set of parameters. Is that a full rank or less than full rank model?
Less than full rank.
Yes. Yeah, because we put levels in for, you know, for each one that we have for the both class variables and the interaction. That's right. So if we consider the L vector, you know, in order to get this specific estimate for group 1 at time 0.3, how would we write that? Well, we want the intercept. We want the first group, right? So if I write this above, we'd have a 1 there, we'd have a 1 there. We're considering the 3rd time point, right? And then there would be a 1 there. So that's the combination of the parameters that allows us to estimate what the first group has at the 3rd time point. And when you write the estimate statement, you partition it by the sources. So instead of writing an L that looks like this, you break it down into intercept, group, time, group by time. It kind of makes it easier, right? A lot of times in R, I think you have to write the actual L vector out. But for SAS, you can break it down by components. Now, if certain factors don't come into play, you actually don't need to write them. Okay? So for example, say we want to compare means between groups at the first time point. The L vector, the linear combination of the coefficients for that we need are given here. And so the first one is going to be for the intercept. And then the next 2 are for group. The next 3 are for time. And then the next 6 are for group by time. Those are the coefficients for those. But you notice we have zeros for time. So we actually don't need to include this. You could remove that, and that's what I've shown below, is you only need to express the coefficients for the factors that have non-zero coefficients. So for this estimate statement, we're comparing the 2 groups at the first time point. And we only need to be concerned about the group factor and the group by time factor. So how, you know, a lot of times when you write estimate statements, it's easier to figure out what the coefficients need to be when you actually work out what you're subtracting from each other. So if we consider the control group at 24 hours, we know we're gonna have a 1 for the intercept, a 1 for the first group. That's the control group. And then the second's going to be myostatin. This is for that application, that specific data set. And then we have times times 1, 2, and 3. And then the linear combination. So this would be C1 C2, C3, myostatin 1, myostatin 2, myostatin 3. Okay, so especially for the interactions, you have to make sure that you remember. It can get confusing, but how do you know like it goes like that? Well, if you have group in the class variable first and then time, then you know that the group is going to be changing more slowly. So you have the group, and then you have time 1, time 2, time 3, and then the second group, and then time 1, 2, and 3. So that's how the corresponding coefficients should look like. So for the control group at 24 hours, we would put a 1 in the first column for group, and then a 1 for the first column for time, and then the corresponding interaction there. And then for myostatin at 24 hours, that would be a 1 in the second column for group, but we still have a 1 in the first column for time, and then you have the corresponding coefficient there. And then you take the difference, and you can see that what happens is we have since the comparison is at 24 hours, and that's in common to both the groups, when we subtract those, that drops out. And that's why we end up with this L vector that looks like this, where we're 1 minus 1, so that allows us a comparison between groups, and then also in the interaction, we have the corresponding 1 and minus 1. So the point of this being that I still do this a lot, where if I'm taking a difference, I figure out what it is for the one thing that I'm subtracting, then the other thing involved in the subtraction, and I take the difference just like this, because then you can see which factors are falling out. Any questions on that? So the last thing I want to do, I'm going to probably jump this one, but I want to show you just one more example of let's do this one for practice. Write out the null hypothesis for we'll do the interaction test here. And I'm going to go to a new sheet here, and hopefully my pen will cooperate with me. So, so again, if we consider the situation, and whether it's the myostatin data or, that was actually not longitudinal data, but you can think of an experiment, a similar experiment, where we have group 1 and 2, and then we have time 1, 2, and 3, and it could be longitudinal. Maybe it is or it isn't. In terms of the test that we're writing, we do it the same way. Okay, so here we have again mu11. Think of things in terms of the means model. So we want to write the interaction test. So we're doing interaction. A way to think about the interaction is, does the difference between the groups change over time? Did somebody have a question? Or so let's do look at the difference between at time 1, mu11 minus mu21. And the question is that the same as the difference at time 2? So mu12 minus mu22. And then comparing at the last time point, mu13 minus mu23. So that's the null hypothesis. So if that's true, there's no interaction, right? That's in the null hypothesis. In the alternative, there's at least one inequality there. So I'll just write HA is the complement. There's something else than that, right? How many lines, how many rows do we need? How many L vectors do we need to do this test? Easy way to remember. However many equations there are, that's how many you need. There's 2 equations. So we have 2 degrees of freedom for this test. So we need 2 rows, okay? So another way to write this would be to write it as move the second one over. So we have mu11 minus mu12 minus mu21 plus mu22. That's equal to 0. And then pick another one. So I'll compare the first to the last. So I'll do mu11 minus mu13 minus mu21 plus mu23 is equal to 0. So this is just reformulating it so that I have 2 equations and we're comparing to 0. So this will allow us to, that's for the means model. For the effects model, I'll let you guys double check this, but it's going to simplify to very similar, but in terms of the interaction, it'll be gamma 11 minus gamma 12 minus gamma 21 plus gamma 22 is equal to 0. And similar for this. What happens to the main effects? They drop out, and I'll let you guys verify that. So I'm jumping a little bit here due to the amount of time that we have left, but you have to remember that mu hj is equal to mu plus alpha h plus tau j plus gamma hj. So I'm using that, and I'll just say check. But those, the alphas and the taus and this mu, they're going to drop out. So you can verify that. I'm going to continue, but I have to go up instead of down. So I'm just going to continue on this page. And I'll get it when I post this, I'll rearrange the order of it. So we have our beta vector is going to be, you put in all of the terms in your model. Right, that's beta. So L, the first L, that's going to correspond to going back down, going to correspond to this first row. So we just have to get the coefficients for that, right? And so we have, it's going to be 0. And then we'll have a 1 and a -1. 0. Then we'll have a -1, 1, and a 0. And that's for that first piece where we're comparing and so I'll put that in parentheses. And then the second one is we have a 1, 0, -1, -1, 0, 1. And that was for the second one. So that was -1, minus -1, 3 minus 2, 1 plus 2, 3 for that row. So when we do a test of C times beta equals 0 versus the alternative, then the C, we need both of those rows, right? So you have the zeros, and then you have the 1, -1, 0, -1, 1, 0, and then the same thing down here, 1, 0, -1, -1, 0, 1. So how do you write that? How'd the estimate statement look for that? If you write this out in SAS, you tell it the interaction. And what would you need in this case? Well, we know that this is for the interaction, this is for group, this is for time, and this is for group by time, right? So when we write this test, the estimate statement, what would it look like? What would be the next thing that we write here?
Would you just need to start with a group by time?
Exactly. So we have group by time, and you can write that out, whatever the actual name that we use, it might be group and time. And then you put the coefficients that you need. So it'd be 1, -1, 0, -1, 1, 0. But we have 2 rows, right? And so that's why we actually can't use, we can't use estimate. What do we have to use here?
Contrast.
Yes. We have to use a contrast when there's multiple rows. There's only one row you can do an estimate, but there's contrast. Now, how do we get that second row? You have to use a comma, right? And I forget, do you write the G times T again or not when you do that?
I think you do.
I think you do too. And then you write the coefficients for that. And then semicolon. So that would be the test. I think you're right. I think you write it again. So that, this is just showing how it works, right? By default, you get an interaction test in the output, but there may be variations that you want to do. Maybe there's 3 groups and you only want to compare interaction between 2 of them. And so you can write your own tests, and this is very powerful. And this is something that I think is very important for you guys to know is how do you write your own tests? You may not just want to go with the default test that SAS or R gives you. So how do you write your own test? And this gives us the ability to do it. And I don't know how much time you guys spent in 6612 writing your own test, but I kind of emphasize it. And you'll see in the next homework, we get to practice a little bit more with that. So we are out of time. I will be around for office hours. I don't know if we'll have a lot of discussion, but we can start out to see if people have things they want to talk about. If my video keeps staying like this, I'll find an alternative way to deal with it and see if I can get the pen to behave better. It seems like once you get going, it does better. Any last second questions you guys have? Okay, so I'm going to get off and I'll join back in at 10:30. If I don't see you, have a nice weekend and talk to you Monday. And just email me if you have any questions. All right, thanks.